All right. So yeah, continuing with SAS activity 5. As a reminder, we were looking at this data set on Taylor Swift's YouTube videos, okay, from her channel. So we had like the number of views for each video, number of likes, number of dislikes, and number of comments. And we're looking at how we can use simple linear regression to explore some patterns in this data set. Okay. So we had, okay, yeah, so we just fit a model. We looked at some summary statistics to start. So there's 133 videos. We see everything's very positively correlated with each other. Which seemed intuitive, so that's always good. Like, as a video gets more views, we would expect it to get more likes. But also, as a video gets more views, we would also expect it to get more dislikes. Right? So everything was checking out there. We looked at, she has different playlists, which correspond to her albums. And so we can see the number of videos for each playlist. Yeah, a little bit of this trend. It looks like the older albums have slightly less videos. And okay, yeah, and we looked at this scatter plot, like coloring the points based on the album. And we can see within an album, it looks like there's probably a linear relationship. It looks decent, at least. And then we fit this linear regression model using the number of views to predict the number of comments. Okay. And then we had our diagnostic plots here. So let's see where we were at. The code, we just left off on 2B, yeah. Salud. Okay, so then did it ask for us to check the assumptions? You know, it didn't. Salud. It didn't ask us to check the assumptions, but let's practice checking the assumptions real quick for 2A. So maybe we'll. I'm going to open up the guide document here to look at what they're, so we can copy and paste the assumptions for simple linear regression. Okay, let's see where the assumptions are at. Okay. So let's like maybe put this in a SAS content just to practice. Okay. Yeah, we've got normally distributed residuals, and it says we check using the histogram and the QQ plot. We've got homoscedasticity, which we check using the residual by predicted value plot. The errors need to be independent of the predicted values, also checked using the residual by predicted value plot, and then linearity, which we can check using the scatter plot of X and Y. And a random sample. In this case, this is a little bit it's kind of a unique setting, I guess. It's almost like we have a census because this was all of Taylor's YouTube videos, so there's not really a larger population. I guess you could view it as like maybe there's other videos she hasn't released yet, so we only saw a subset of the ones she makes. I guess you could do that. we'll assume this is met. In reality, yeah, it's a little bit violated, I would say, because there's, like, if you dig into the data, there's some videos that are for like the same song. So there's kind of duplicates in a way. There's like Taylor's version of some song and then another version of the same song. Some of them are like live performances, I think, versus the recorded version. So they're not really all independent of each other, but it's hard for this assumption to be truly met, I think, in many scenarios, but you often just try your best. Okay, so we'll say, since these are all separate videos, we proceed under an assumption of a random sample. Okay, so yeah, now these other ones we can actually check using the SAS output. So let's start with a discussion of normality. Okay, so for checking the rest of these assumptions, we're always going to use these fit diagnostics, these diagnostic plots, which SAS always gives us like this 3x3 grid. And so which ones are we going to use for checking normality? Which ones of these 9? The histogram and the QQ plot, right? Those are the 2 that we use. And so, yeah, as a quick review, I give examples of like, here's how it looks when normality is met. And then these are 2 cases where it's violated for the histogram. And then for the QQ plot, here's how it looks when this data is perfectly normal, like this data actually came from a normal distribution. So notice it's not perfect. And then here's how it looks maybe when it's violated. Okay. How does ours look here? Yeah, it's peaked actually, which is kind of interesting. So this is interesting because I think without the QQ plot, and if you didn't have the density curve on here, you would almost think, or like I thought, this looks pretty normal. It's like a bell shape. It has one peak. It's pretty symmetric. You would think it checks a lot of the boxes you're looking for in normality. But then when you look at the QQ plot, it looks awful. So that's why it's usually good to look at both. Sometimes something can be hidden in one plot or the other. This is generated from what's called actually a Cauchy distribution, which is a bell-shaped symmetric distribution as well, with one peak. It's very similar to the normal, but actually, when you look at the QQ plot, it's very non-normal in a way, I guess. So anyway, yeah, it looks like this pattern right here is like similar, kind of similar to what we're seeing here. It's like a Cauchy distribution, which is interesting. So yeah, main takeaway. Let's see. Get back down to the assumptions, right? So yeah, the residuals have a very peaked distribution violating normality. And we'll say, to be clear about why, as shown in the QQ plot, where many points stray from the diagonal line. So always good to cite exactly why it's violated. and which plot we looked at. What about the homoscedasticity assumption? How's that looking here? Pretty bad as well. Yeah. So yeah, as a reminder, in the homoscedasticity assumption, okay, I give some examples here. Like D, it's met because we have a constant vertical spread from left to right. C, it's also met, actually, for homoscedasticity. I hope my laptop's in. Yeah, should be fine. Yeah, we can have outward fanning in the top row. That's what's going on here, so that's violated. And that's what we've got going on here. This is like even pretty extreme. It's worse than the examples I gave in the document there, because it's like, here's like the vertical spread going out. It's fanning super quickly. So yeah, really bad here. The general idea of like what we're looking for here in regression is that how much our predicted values are off, which is described by the residuals, should be constant for any predicted value. But what we see is like for small predicted values, our error is really small. But then when the predicted value is really big, the error is really bad. So that's what messes up the theory underlying inference and other things we do with the regression model. So yeah, there is a clear outward fanning pattern. It's nice to have spell check in Google Docs, and then you get something like this. It just makes you feel like you're awful. I think. Okay, and then for independence, okay. Yeah, again, I give these examples in the guide document. So we're looking at the same plot, residual by fitted value or predicted value. And what we want to see is we're trying to check if the predicted value is informative of what the residual will be. So in the, let's see, in the right column here, these are both meeting the assumption of independent errors. Like if we knew the predicted value, we don't really have a good guess as to what the residual would be in either of these. But in these ones, it's a little bit harder to see in this top one, but you can see like if the predicted value is small, the residual is always negative. If the predicted value is big, the residual is always positive. So knowing the predicted value would tell us something about the residual. And same with up here. It's a little bit harder to see, but it's all negative over here, slightly more positive over here. Okay. And so that's one case in which this is like the residual and predicted value have a linear relationship themselves, which is bad. So that violates the independence assumption. You can also have nonlinear patterns, and that still violates that. So here's like a quadratic pattern, and then sometimes I've seen this only like once or twice in real data sets. You can even have like a weird, like oscillating pattern. Like this is like a sine function, okay, which these also violate the independence assumption. So here, salute. Let's see. Does it seem like the predicted value gives us a good idea about what the residual would be? Like, no, probably not, actually. So homoscedasticity looks awful, but independent errors, that's the one assumption that looks fine, I would say. So there is no clear pattern and then for linearity, that one's a little bit, I don't know if there's a clear takeaway here. I mean, it doesn't look like, if it's not linear, I'm not really sure you would describe it as anything else. Like maybe quadratic or exponential with like a curve up, I guess, but we'll say usually, at least this is what the textbook claimed, that if if this assumption is met, where there's no pattern, predictable pattern in the residual by fitted value plot, one of the textbooks that was suggested for this class said you can then assume there's a linear relationship, which I don't know if I buy that, but I guess maybe it's just a little bit extra confirmation that we can, okay, maybe assume there's a linear relationship here. So we'll say this is where we'll use that like cautionary language, I guess. So there is a somewhat linear relationship between a video's number of views and its number of comments. Okay. But the main takeaway, just like with ANOVA and the other models, is that overall, since not all assumptions are met, and yeah, the purpose of that is that, or the takeaway from that is that p-values associated with the model or confidence intervals are not reliable anymore. I can make it a little bigger. And is that big enough for people in the back? Okay. Any questions about how we checked those assumptions? Practicing that again, because that's something you'll have to do on the final exam for sure, and on the homework. So, okay, so getting the estimated slope and intercept from the output Here we're looking for this table that has a column called parameter. I found that's the best way to find the table with the regression estimates. So here is our intercept, and here's our slope. So put those values here. I'm not going to type them here, but there's our two numbers. Let's see what it asks for next. Provide the values of, oh, I didn't ask to interpret them. Let's interpret them in context. Okay, so I guess I will put the values in. So again, just for practice, let's think about, which means that, or actually, let's think about the intercept. So we talked about this last time, how it's inappropriate to interpret it in this context. Oh, so we'll just mention that. So since 0 views outside the scope, because X is the number of views. Yeah. So that's what we could say about the intercept. And then what could we say about the slope here? How could we interpret that? Yeah. Right. Yeah, exactly. So and so yeah, this is a good example of like it's a little bit weird to say it this way. How could we like tweak that to maybe be like a little to still say the same thing essentially, but maybe have it be a little more understandable for people who don't like decimals, maybe. Yeah, you could do it as like a percentage. That'd certainly be one way. How could we say this like using whole numbers? The same thing. Yeah. Yeah, exactly. And so you can totally do that. Like it's valid to say like instead for every 1,000 views, we would expect a video to get and then multiply this number by 1,000. Okay, so you'd end up moving the decimal 1, 2, 3 times. So that just makes it a little bit more understandable. It's roughly like every 1,000 views the video gets, it'll get one comment. That shows you the maybe part of the problem with looking at the comments and thinking like, oh, that's what people are thinking. It's like, well, that's 1 out of every 1,000 people who watch the video. That's their thoughts, but maybe other 999 people probably don't feel as strongly about the video. That's like social media in general, right? All right. Okay. Yeah, so now we can look at part C. So we saw this with the ANOVA data set when we looked at survival analysis for one-way ANOVA, for like the survival time by the cancer types. The common thing that people do when the residuals are right skewed, which is kind of the case here, is to use a log transformation of the response variable. Okay. So let's do that. We're going to calculate a log transformation of the response variable, which is the number of comments. And then we're also going to calculate a log transformation for the number of views, which is not obvious why we would do that yet, but let's just take my word for it now. So we don't get a ton into data manipulation in this class. We're more just like fitting models to data that's already ready to go. But if you go on to take like Stat 318, you'll learn more about data manipulation techniques in SAS to like get it ready for modeling. So we're going to do that a little bit here. We're going to make some new variables. Using what's called a data step. So data steps, you start with data instead of proc, and then you say the name of the new SAS data set that you want to create. So we're picking out the name. So we can call it something like Taylor new. Okay. And then just like when we import data using proc import, SAS is very conservative about like, oh, if this already exists, I'm not going to overwrite it. I'm just going to run your code and leave whatever already existed. But usually when you run the code, you want it to actually implement what you submitted. So we have to add this replace option to say, hey, make sure you actually run this no matter what, to override that default behavior. Okay. And so all this code does so far is says we want to make a new data set called Taylor new, and we want to replace it if it already exists. Commonly, what you do when you make a data set like this with a data step is you start with a duplicate of an existing SAS data set in your environment. So you do that with this set statement, saying like start with a duplicate of, and then here our data set we were already working with is called Taylor videos. Yeah.
Is the capitalization?
Not for this. Yeah. SAS is generally like case agnostic, we would say. Like it doesn't care unless, except for like in strings like this, that's the only time. So this will make a new data set called Taylor new. If you look in the libraries tab over here, this is actually, we haven't looked at this before, I don't think, in this class. This is where like the SAS data sets in our environment are like stored, they're hanging out. So if you click on that and click on my libraries, there's actually like sets of data set over here. There's some for like, yeah, maps, like example data sets here. The default, like when we make data sets or we use like proc import to make new ones, they all get thrown in this work library. And so you can actually see, if you open it up, you can see the data set that we made here, Taylor videos already. And you can open it by like double clicking on it, opens it kind of like Excel. Okay. So after we run this, we're making another data set called Taylor New. It's an exact copy of Taylor videos. And so if you run it and then after the fact look, you can now see, oh, and I made one called replace. Maybe there's something wrong with that syntax, so I'm using that, but I think that's the correct one. Yeah. I don't think that one. Yeah, that doesn't. Okay. To look into that. But yeah, this makes a new data set. Okay, which you can see over here. Taylor New. Okay, but if you open it up, it looks exactly the same as Taylor videos right now. So to make a new variable, we can, it's like the general syntax is new variable equals some function of an old variable. Like it could be like 2 times the old variable, or the square root of the old variable. SAS has like many functions like that. So we're going to make a new variable called log views that's equal to the log of, and the variable is called view count if we looked it back up. And by default, it's like the I believe it's the natural log by default. Googling it real quick. Yeah, it defaults to the natural log. So for those familiar, there's different kinds of log functions that are slightly different, but this one's the natural log. Right. So now if you run this, okay, so you could look, before running this, you could look and see, like, oh, it's the same variables as before. There's no like log view count variable, but then after you run it, and you look at the data, oops, look at the data, you can see it tacks it on to the very end, the log number of views. Any questions about how we made that variable? Okay, yeah. Oh, is it? Oh, that's true. It's like jumping. Well, actually, Yeah. Um, oh yeah, so look at it. So now we look over here. See, there. Um, oh, okay. And then it's like, oh, okay. So yeah, yeah. And for some reason, it's like defaulting together. Put it in there, and then do the Taylor new. Yeah, should be.
Okay.
Yeah, great. Anybody else have any errors? Okay. Then, okay, so when you make a new variable, you need like one statement like this. So we're going to make another new variable in the same one that is the log comments. So we can copy it just like this. Let's see if we're going to make it. Oh, it's going to be close. Okay, well, we'll see how far we get today. Okay. So we're going to paste it in here. It takes like USB-C, but I'll just start up this like lab one. Thanks. Yeah. Oh, that's probably okay. Thanks. Maybe we'll see if it makes it. It's still got 10%. But thank you. Yeah. So log comments, we'll do it like that, and then comment count. All right. And then if we run that, we should be able to see again in the Taylor new. Now we have this even additional column. And so log transformation again is nice because if you have this like so just to show like real quick. Okay, we can have a histogram of like the views. We look at like a histogram of the views, not transformed. Okay, here's how it looks. Super right skewed, right? Same thing if we looked at like the comment count. If you look at the distribution, super right skewed, which is very much expected for this type of data. Like if you're looking at the number of comments on a video, it's like it's going to be really close to zero potentially for some videos, and then some videos just are extremely popular. So this is not surprising to see this type of distribution. Yeah, what's helpful about the log transformation is that just doing the log, you get, it's still going to be skewed right. that's what happens after the log transformation to the distribution. So it's more normal than before. It's still not normal, but the skewness is certainly like not as bad now. So that's why people like this log transformation. Okay. So we're going to show how, yeah, we can refit using just log comments. So just the log transformed response, but we're still going to use the regular views as our explanatory variable. And we're going to show what that looks like. This is essentially the process I went through when I was looking at this data. Is honestly, I thought, oh, we just need a log transformation of the views or the comments, since that's our response variable. Usually that takes care of it. Okay. Yeah, let's copy the proc GLM code from before, because actually it's going to be the same exact code. So this was from like 2A, and then the only thing we're going to change. So what do we need to change in here if we want to use a log transformed response? Yeah, the model statement will say log comments instead of comment count, and that's all we need to change. We're just going to start with just the view count, because actually this is what's traditionally done, just a log transformation of y, and then that's it. Yeah. Oh yeah, you're right. Good call. Yep. Yeah, that would probably have an error otherwise. Yeah, let's see what the error would look like. Yeah, it says it can't find that variable because it's not in there, so we have to, yeah. Good call. So yeah, make sure to update our data set name and the variable name there. And then we can look at the output. So let's see how it looks now. We won't like formally recheck all the assumptions, but we'll just talk about it real quick here. So how does like normality look now? Yeah, it looks really good actually, which is why people do this, in part why they do this log transformation. Like this looks great. The histogram looks a little weird, but the QQ plot is more reliable, I would say, and that looks great. How about homoscedasticity though? Yeah. There's like funneling now, almost. If you just kind of, I did not expect this. It's almost like it's going like that, where the spread is getting really small. So it did not solve all our problems. I would say it's still maybe independent, but independent errors is still okay. But now it's like normality is met, independent errors is met, but we're still don't quite have homoscedasticity. And then here's the bigger thing that I saw that made me think we needed another transformation, is this linear in the scatter plot now? No. So usually after the log transformation like that, you would hope it looks very linear. This is like worse than before. Okay. So yeah, we're kind of in a tough spot here. But has anyone used Wolfram Alpha before? Yeah, Wolfram alpha is super useful. So let's see like what our boundaries are here. 0 to 1 times 10 to the 8th, I guess. We'll just say plot that from 1 to 100, like that for log x. Here's how the function, if you plot x by log x, here's how it looks. It's like a mathematical function. And so when we look at our scatter plot, you see how that pattern shows up here? It's just like the log function. And so what that's telling us is that if this is our x, this is log of x. Which gets a little bit like that's kind of strange. There'd be a couple things it could imply. I played around with it a bit and found if we log transform this one as well. Okay, let's see how that looks. Essentially for part 2E. It's always good to look at the plot so you can identify issues like that. For 2E. Oops. Just going to copy that model code again. And now we say log views. Okay. So log transformation of both. If we look at the output for that, how are we looking now? Like, how does normality look now? Looks awesome. Looks really good. And then independent errors. How is that looking? Did we ruin that? No, it still looks good. I would say you can't really tell what the residual is going to be using the predicted value. And then how about homoscedasticity? Looks pretty good. So the double log transformation, which I had never used before or never actually seen, seems to fit this, help this data really well. Also, we didn't even talk about outliers and influential points, but like now there's no influential points either. And there's no extreme outliers. I mean, there's some that have values bigger than 2 for the studentized residuals, but this is not bad. And then more importantly, when we look at the fit plot, the linear relationship looks good now. So log views by log comments. Yeah, seems to fit this data well. Okay. And so yeah, what this means exactly, like you can work out the math, how that implies like X and Y relate to each other. I had to sit down and write it out. But I mean, so for a regular linear regression model, we have that Y hat or Y is equal to like beta 0 plus beta 1 times X plus an error term. And so when we log transformed both, now we're fitting like a model like this. Okay, or maybe we'll call it like beta 1 prime and or B0 prime, B1 prime plus this new like, because these are different than the original model that we show. Or maybe we'll do it together. Less typing. These are our first ones. Here's what we get in the double log. We'll call it like the power log, because that's actually what it's called. And then what this implies, like if you think about how y changes based on x, to undo the log function, does anybody remember how we undo the log function? If it's log base 10, you can do 10 to the power of it. Yeah, and for the natural log, we do e to the power of both sides, yeah, which is called like the exponential function. So if you do that, that undoes the log, and then you have e to the power of e0. And I'm sorry, to make clear, you don't have to go through all this. Like, I'm just showing you. We won't be tested on this at all. Okay, and then just using math, that implies that y is equal to e to the beta naught times x to the beta 1. And it's like times e to the residual term. Oh, there's two e's in there. That's not okay. Maybe I'll call it like, you know what I'll do? exp sometimes people use for the exponential functions. Yeah. Okay. So this is like the implied model for how the views on a YouTube video relate to the number of comments, is that the number of comments is equal to like the number of views to some power, which is, this is the slope that we get from the SAS output, times e to the intercept term that we get from the SAS output, and then multiplied by some error factor. So the error is like multiplicative. For this type of model. So it's kind of interesting because this seems to be what fits the data well, apparently. So it's not quite as simple as one might expect, but anyway. So yeah, I'm not going to test you on that, but it's just kind of interesting that that's what shows up in the data. And when you look at Olivia Rodrigo's data, it's the same. I would assume this holds for like all kinds of YouTube videos. And I was trying to think about why that's the case. I guess I'm not really sure, other than like maybe somehow with like how the YouTube algorithm works with like, it's like a feedback loop, like videos that get more popular, it sort of like cascades on itself. So it's not really linear in how it's growing. Maybe it's, yeah, that rate of change is like much faster. So that might have to do with how this is showing up in the data. Not sure. Anyway, so we will just take it for what it is and Yeah, this pattern that we're seeing, how X and Y are relating to each other, the views and comments, follows apparently what's called a power law. There's like a whole Wikipedia page about it.